All right, this is a video on how do we calculate all the different ways a Rubik's Cube can be mixed up. We want to know all the different combinations possible. This is a video on explaining the math behind that, how we can figure that out. There's a couple things to take into consideration real quick. First of all, we have three different types of pieces. We have centers, corners, and edges. Cube is 3 by 3 by 3, so 3 times 3 times 3 is 27, but we don't have a cubey in the middle, so we subtract that by 1. That gives us 26. And also the centers don't move. The centers don't move in relation to one another because they're screwed into a core, so they're fixed. So the math that we're coming up with has nothing to do with that, the centers. And there's 6 sides, so we're talking about 20 cubes walking around. 12 of them are edge pieces with 2 sides, and 8 of them are corner pieces with 3 sides. So let's talk about parity real quick. So if we were to take this cube, put all the pieces in randomly and try to solve it, the odds of it being solvable are 1 in 12. And the reason is certain things won't come up. On a solvable Rubik's Cube that you mix up and solve, certain things won't happen. So you won't see something like this happen, where you have a corner that's permuted right. It's in the right spot, but it's oriented improperly, and there's only one of them. This is also the same problem, or a corner twist parity, because this is twisted clockwise in the wrong direction, and so is this. Now if I twist 3 of them clockwise in the wrong direction, that's not parity anymore, because clockwise plus clockwise plus clockwise equals up. So I could do this and get them all flipped. And that's not parity. Or if I had one clockwise and I do one counterclockwise, they cancel each other out too. So that's not parity. That's a solvable cube. That's an A-perm. So the odds of just putting a cube together randomly and having it being solvable just with the corners alone, being twisted with corner orientation, is 1 in 3 for it being solvable. So you take it apart, and if that was our only problem, but we have other issues. Edge orientation. This is permuted properly, this edge. It's in the right spot, but it's flipped. It's oriented improperly, and it's the only one. This will never happen either. Edges always become oriented or not oriented in even numbers. So if you move a face, all 4 of these edges are out of orientation. I could actually just rotate the cube, and all of these are oriented again. They're not in the right permutation, but they're oriented. Now they're not again. But either way, it's always going to be 2, 4, 6, 8, 12, 10, or 0. It'll never be 1, 3, 5, 7, 9, or 11. But we only count this as a 50% likelihood because if you have 5 edges that are not oriented, it'll always reduce into 1 at the top. Once you reduce the cube up into the top layer, it'll always end up just being 1. So it's a 50% chance. Half the time this is going to happen, and it's not solvable. You'd have to take the piece out and flip it. That's how you fix that. There's no moves you can make for that to be flipped. So that brings the 1 in 3 and then the 50% into 1 in 6 likelihood of it being solvable. This is another parity where you just have 2 edges. They're oriented right, but they're not permuted right. Everything else is solved. This will never happen either. And let's see, I can do a R-perm, and I can fix them. But what you see is now I got 2 corners that are out. So it's the same problem. So I'd constantly, every time I try to fix one, something else will pop up. See, I could do a T-perm, it'll flip these, but it's also going to flip these. Because 2 pieces flipping without changing permutation or orientation will never happen. It's impossible. So that's the other one. There's a 50% chance you're going to fall into this. Whether it be corners or edges and just 2 of them, it's the same problem. You can always, I can make it be any 2 corners on this cube or any 2 edges with what I have right here. So that's a 50% problem. So the likelihood of it being solvable are 1 in 12. So we're gonna do our math with our corner and edges because again, we don't have to do anything with the centers because the centers don't move. And then we have to divide it by 12 to deal with this parity situation. So let's talk about corners. There's 8 corners, and then this can go in any one of 8 spots. The way we do that math is we write an 8 with an explanation point, and that represents 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That number is 40,320, 40320. The way we get that is it can go in any one of these 8 spots, so that's 8 possibilities. But then once it's in one, and we grab our second guy, it only has 7 possibilities. We put that in any one of those 7. We grab our third piece and it only has one of 6 until we get to the last piece where it only has 1 possible place. So that's why we have an 8 factorial there. So that addresses corner permutation, where it can be, which position it can be in, but it doesn't bring up how it's flipped. So we have to multiply this number by 3. There's 3 different colors. You can go in any one of 3 ways. And each one of them can do that. So to the 8th power. So we write it like that, 3 to the 8th power. That number is 6,561. So this deals with our corners. Now we got to deal with the edges. So with the edges, there's 12 places these can be. So then we do a 12 factorial, just like that. And that number is quite a bit higher. It's 479,001,600. That's your 12 factorial. And then we got 2 sides, which is 2 to the 12th power. Just like that. And that's 4,096. But then we have to divide it by 12 because of our 3, 2, 2. 3 times 2 times 2. Like that, which is the same as 12. So let's do that math. 8 factorial is 40320. Multiply that by 3 to the 8th power, which is 6561. Then we have to multiply that by 12 factorial, which is 479,001,600. And we multiply that by 2 to the power of 12, which is 4096. And what we end up getting is 519 quintillion, which is 519 billion. Multiply that by another billion. But we have to divide it by 12. What we get is 43 quintillion. What this number actually is we got 43 quintillion, 252 quadrillion, 3 trillion, 274 billion, 489 million, and exactly 856,000. That's the number of combinations a solvable Rubik's Cube can be in. This number, to put this in perspective, these cubes are a little smaller, but if these were 6 centimeters or 60 millimeters, this one's, I believe it's 55 and a half. But if it was 60, you took and you had one Rubik's Cube for each one of these combinations, you could cover the surface of the Earth 300 times. The reason I'm bringing this up is because I find it interesting, and also I want to talk about this guy next. and I want to talk about parity. And the math for this is quite a bit different. Not only that, the centers do move on this. So there's quite a few different things that can come up. But some of the parity that cannot happen on these things can happen on this, because we're building these, and we could build this and have it flipped wrong and have an odd number of edges. So we have an algorithm to deal with that. Or we can just have two edges that need to be dealt with. There's two. We can make that happen without taking the cube apart. So we want to talk about how to do those. Or something like this. This is the Red Bull algorithm, where we have edges out. That's it.